Now let's talk about example 22.9 on page 457 in the text. Here's a Doppler example, and what you're given in this problem is that the speed of sound in air is 340 meters per second. So you're not given the temperature and then asked to solve for the speed of sound in air. In this problem, it's just given to you. You're also told that there is a train whistle, and that whistle is producing a sound of 400 hertz. And you're also told that the person listening, or the observer, is stationary. Two-part question. The first question is, as the train approaches the observer at 20 meters per second, what frequency is heard by the observer? So let's use our general Doppler equation. Frequency heard by the observer is equal to the frequency of the source times speed of sound in air plus the speed of the observer divided by the speed of sound in air minus the speed of the source. The train's approaching at 20 meters per second, so that ends up, our sign convention tells us that that is a plus 20 meters per second. And we also know that we have a stationary observer, so the speed of the observer is 0. So let's go ahead and plug in what we know. Frequency heard by the observer is equal to the 400 hertz, that's the frequency of the source of sound, divided by 340 plus 0, divided by 340 minus a plus 20, because we have an approaching train, so you plug in the speed of the source as a plus 20. I haven't put units in here. All these units, numerator, denominator, are in meters per second, and they're all going to cancel out. So then you end up with the 400 hertz times 340 divided by 320. And you can see in the text that results in 425 hertz, which is the frequency heard by the observer, even though as the train's approaching, the source of the sound continues to be 400 hertz. This is just the frequency that the observer hears because of the approaching situation. So when you do these kind of problems, you should have an idea ahead of time what kind of an answer you're going to get. For example, if we did this problem and did something incorrect in the equation, and let's say your answer turned out to be something less than 400, then you'd have to be able to recognize that that answer would not make sense, because in an approaching situation, the frequency heard by the observer should be a higher frequency than what the source of the sound is putting out. So in this case, this number does make sense in terms of the frequency observed being higher than the source of the sound. There is a part B to this problem. Part B is what happens, what is the observed frequency if the train is moving away from the observer at that speed? So part B, we don't need to rewrite the whole problem. So what frequency is heard by the observer when the train is moving away from the observer at 20 meters per second? In this case, that 20 meters per second is a negative 20 meters per second because the train is moving away, and that was our sign convention. So in this case, the frequency heard by the observer Now, the only thing we have to change in this problem now is the sign of the speed of the source. In the denominator, it's now 340 minus a negative 20. And that ends up being 340 plus 20. So in the denominator, you now have 360. And when you do that calculation, you now get 378. And again, that number does make sense because in a moving away situation, the frequency heard by the observer would be less than the frequency of the source. Now, what you also have to understand too is that as this train is approaching the observer in the part A of the problem, the sound of the source of the sound gets louder to the observer, and as the train's moving away, it gets fainter. But in terms of frequency, whether the train is a mile away approaching at 20 meters per second or 100 feet away approaching at 20 meters per second, then in the approaching situation, the frequency heard will be 425 hertz. And in the moving away situation, when the train has just passed the observer and is 100 feet away, or when it's 1,000 feet away, the frequency heard will be 378 because in both of those cases, the train is moving away from the observer at 20 meters per second in this case. Now, certainly when the train gets 1,000 feet away, the actual volume or loudness of the sound will be less, but the frequency won't be changing. Now let's take a look at the last example in chapter 22. Again, on page 457, example 22.10. This one's a little bit different. Once again, you're given the speed of sound in air at 340 meters per second. And the source of the sound is from a car horn, and that's putting out a frequency of 360 hertz. Now, this one really requires a sketch to understand what's going on. So you're given that there's a car that's traveling to the left at 20 meters per second. And it's blowing its horn at 360 hertz. And then there's a person in front of the car riding a bicycle who is riding to the left at 12 meters per second. So you have this bicycle in front of the car traveling in this direction, same direction as the car, at 12 meters per second. So in this case, the speed of the observer is 12 meters per second. And do we assign it a positive or a negative value? In this case, we're going to assign it a negative value because the observer on the bicycle is trying to move away from the car. So it's not intentionally approaching, it's moving away. Then for the car, the speed of the source is 20 meters per second. And with respect to the bicycle, it's approaching the bicycle. So we're going to assign that a positive sign. And the question becomes, what frequency is heard by the person riding the bicycle? So let's use our general Doppler equation. Frequency observed is frequency of the source times speed of sound in air plus the speed of the observer divided by speed of sound in air minus the speed of the source. So let's plug in our numbers. The source frequency is 360 hertz. Speed of sound in air is 340 meters per second. Again, I'll leave the units out since they're all going to cancel out. And it's plus the speed of the observer. And in this case, speed of the observer is negative 12. So it's plus a negative 12 And then in denominator, 340 meters per second minus the speed of the source, and it's a plus 20 meters per second. All right, so now that you have it set up, now it's very similar to the previous example. And whereas the previous example had two questions, both approaching and moving away, this is, you're only asked for the frequency heard by the observer in this moment. So if you do the math, then it turns out to be 369 hertz is the frequency heard by the observer. Now, does that make sense? So the car is approaching the bicycle at 20 meters per second. The bicycle is moving away at only 12 meters per second. So the sum of that is that the bicycle and the car really are moving closer together, which means that a higher frequency heard than the source does make sense in this case. So here's your assignment to practice the Doppler effect problems. 3 problems at the end of the chapter on page 461, problems 27, 29, and 31. Just a note about those problems. If you take a look on page 461, there's a note just before the Doppler problems start. It says that you're assuming the speed of sound in air is 343 meters per second for all of these problems. So in each of the individual problems, you're not told what the speed of sound in air is, but we're assuming it's the same speed of sound in air, 343 meters per second for all of those problems. Another note is you'll notice on problem 29, you're given 3 answers. You really only need to calculate 2 answers there, in the approaching situation and the moving away. The second answer you're given only happens for the tiniest fraction of a second when the train and the observer are even with each other. It's really not even worth considering at this point. So because the frequency heard in the approaching changes almost instantly from the approaching to the moving away situation. So just the first and the last answers on number 29 is fine.